Okay, so let's start. It's a pleasure to have now Eric Lescano with his first lecture on alpha prime corrections and their double formulation. We must be very grateful to Eric because unfortunately he had to cancel his trip to Santiago. He's now lecturing from Buenos Aires. It's very early in the morning, so many thanks, Eric.
You're welcome. And I would like to start saying thank you very much to all the organizers. This school is amazing. And okay, to the audience, I hope you enjoy these lectures about alpha prime corrections. And I'm going to start with a brief and general overview of the whole course. In the last decades, there has been a huge progress made in the study of the low energy limit of string theory. I'm going to highlight some important things. This low energy limit of string theory was already studied in this school. For example, in Gianluca's lectures, you have studied 11-dimensional supergravity, 10-dimensional supergravity for type 2b. And these kind of theories are known as supergravity theories. And the important point here is that these theories describe particle dynamics. So let me highlight this. These kind of theories describe particle dynamics. Many times I am going to write Sugra instead of supergravity, Sugra, and these kind of theories describe particles. So describe particles, and this means that the string structure is completely suppressed. We are not seeing a string structure when we study supergravities. So the spectrum of string theory contains a tower of states. If we consider the physical states, we have on the one hand the massless states, massless, and on the other hand we have massive states, but these massive states are ultra massive states, are very, very massive. So from a phenomenological point of view, it is common to focus only in the massless states, and we are going to integrate out the massive ones. We are going to integrate out these states. We are not going to consider these states, or we are consider them, but we put them on shell. We integrate out these massive ones, these massive states, and this procedure gives rise to a particular higher derivative structure. So we focus only in the massless states, we integrate out the massive ones, and this procedure gives rise to a particular higher derivative structure. This higher derivative structure corrects the low energy limit of string theory. This means that we are going to correct a supergravity. So the study of these alpha prime corrections is the main study of these lectures. And what I am saying is that if we have these kind of actions, for example, if we have some supergravity action, like this one, you have seen this action with Gianluca. If we have this supergravity action, this supergravity action contains for us alpha prime corrections, higher derivative terms over here. These are alpha prime corrections. These alpha prime corrections are higher derivative terms that appear when we integrate out these massive states that string theory contains. So this is the main topic of these lectures. And let me continue with this general overview. Please ask questions whenever you want. Interrupt me. It's completely okay. And if you need a different slide, just let me know and I can go up. Here we have some examples where alpha prime corrections are important. For example, testing duality conjectures. When we want to test a duality conjecture for string theory, we need the whole story. So we need the alpha prime correction. So this is a first example. We have microstate counting of black hole entropy. We have moduli stabilization, the Schwarz program. Of course, we have double field theory. We are very interested in double field theory in these lectures because we want double field theory to obtain these alpha prime corrections. And inside this topic, inside double field theory, we have different topics or different topics where alpha prime corrections are relevant. And these topics are very related to the topics of this school. We have generalized T-duality, different generalized T-dualities. For example, abelian, non-abelian, Poisson-Lie dualities, deformations such as Young-Baxter, and for example, classical double copy. These are topics where alpha prime corrections are very, very important. So in this kind of topics, we need the string structure in our effective theories. So this higher derivative structure was historically computed using a scattering amplitude. This is a first method to obtain alpha prime corrections that we are going to study. Scattering amplitudes. These scattering amplitudes are related to, let me change color. These are related to interactions in string theory. This is the first method I am going to tell you about. It's scattering amplitude. In order to use this method to compute alpha prime corrections, we need string theory. We are in a string theory. And there exists another historical method that is the beta functions computation, but it's a different method. Both are very popular. And in this case, when we use beta functions computations, we are trying to preserve, we preserve local Weyl invariance at the level of the worksheet. This is worksheet level. So these kind of procedures were very, very popular. And with these procedures, we know many, many terms that corrects the effective action of string theory in its different formulations. So in the last years, many people start using double field theory as an alternative method. This is an alternative method. Particularly, this method doesn't use string theory. We always need to compare this double field theory alternative method when with respect to the other method. We need some comparisons, since double field theory is not particularly a string theory. So it's an alternative method, but we need comparison with the standard methods. This will be clear perhaps in the second lecture, but this is just a general overview of the whole course. So in these lectures, we will review some advances in this direction, and I am going to show you that from double field theory, we can recover some terms related to a string theory, some terms that correct the low energy limit of string theory. Okay, here you have a small plan for these 3 lectures. Today, we are going to analyze the 4 derivative gravitational terms. This is important because we are not computing all the terms, all the 4 derivative terms. We are computing only, or we focus on the gravitational terms only, and in 4 derivatives gravitational terms in bosonic and heterotic supergravity. On Thursday, we are going to review higher derivative double field theory. I am going to give you a first proposal to obtain higher derivative deformations. And finally, on Friday, we are going to analyze a systematic procedure to obtain this higher derivative double field theory. At the end of the day, we want a systematic procedure in order to find the alpha prime corrections. So this is the plan for the whole week. And let's start with some motivation. I am starting from the very beginning. If you have any question, go ahead. In string theory, we replace the idea of point-like particles with extended objects. These extended objects, of course, are strings, but we have also branes. And in this kind of formulations, gravity and gauge symmetries coexist. Here, I am going to highlight some characteristics of string theory. For example, string theory is unique. We have different formulations. For example, we have closed strings, we have closed strings, we have open strings. Since we want gravitational terms, we are going to focus on the closed strings formulation. We have different formulations over here. We have bosonic string theory, bosonic string. We have type 2. You know that there's a type 2A and a type 2B. We have two different type 2 theories, and we have heterotic string. Sorry, heterotic string. We have heterotic string. The heterotic string is a combination of the bosonic string and the type 2 superstring. Particularly, it's important for you to know that this theory is supersymmetric invariant. The amount of supersymmetry is in n equal 1, and sorry, n equal 2, sorry, n equal 2. And heterotic string is supersymmetric invariant, and the amount of supersymmetry is n equal 1. While bosonic string contains only bosonic degrees of freedom, we don't have fermions fields in the spectrum, so it's not supersymmetric invariant. Recall that a supersymmetry invariant theory is a theory that contains both fermions and bosons, and there's this symmetry, this supersymmetry that mix the bosons and the fermions. So type 2 is a supersymmetric theory. The amount of supersymmetry is n equal 2. A heterotic string is a combination between the type 2 and the bosonic string and contains supersymmetry, since type 2 contains supersymmetry. So we have n equal 1, and bosonic string doesn't contain supersymmetry. It's not invariant under supersymmetry rules. This will be important for our discussion, but we are not going to introduce fermions in these lectures. We are always forgetting a part of the Lagrangian or of the transformations when we talk about, for example, about the type 2 or the heterotic case. I will be more clear in next slides. So, and of course, we are not studying open strings because we want to focus on the gravitational terms, and the gravitational terms are present in the closed strings. So let's talk about closed strings. And we have only one free parameter in a string theory. All the string theory formulations contain only one free parameter, and this parameter is alpha prime, the parameter that is important for us. This is only a free parameter, and this is very different, for example, with respect to, I don't know, the standard model. In the standard model, we have 19, 20, I don't know, a lot of free parameters, and in string theory, we have only one parameter. This only parameter is alpha prime, and this means that, for example, the critical dimension of each formulation of string theory is fixed. We can't define, I don't know, bosonic string in 20 dimensions. For example, bosonic string, again, bosonic string is defined on a 26, on D equal 26. The target space, the strings are on a manifold, and this manifold is a 26-dimensional manifold. It's important, this number, 26. The number for type 2, the critical dimension of type 2 theories, is D equal 10, and the heterotic string is also D equal 10. This last 10 is related to this 10, because if we want to combine bosonic string theory and type 2 superstring theory, we have to have the same dimension. So the heterotic string theory is also defined on a D equal 10 target space, D equal 10. Okay, finally, you may know that the different particles appear because the string has different modes. So we have, recall that we have massive states and massless states, and we are always focusing in the massless one, and we integrate out the massive states. So we are going to consider always that we can expand in order of alpha prime potential, in order of alpha prime, sorry, we can perform this expansion. This means that all this target space contain curvature. R is the curvature of all these manifolds, is the curvature, and we are always studying in this limit. We always can correct with alpha prime, with an alpha prime expansion, our theories. This is our limit. We consider that the square root of alpha prime that has length units over R is a tiny number. So we are working in this limit. And here you have an example. If we focus on bosonic string theory, recall that in this case, D is equal to 26. In Gianluca's lectures, these fields have appeared. You have a metric tensor, a two-form, and a scalar, the dilaton. Let me erase this. You know the field state. These are the massless states of bosonic string theory. All the massive ones are integrated out. The fundamental fields are a metric tensor, a two-form, and a scalar. This two-form over here has a curvature. The three-form, H mu mu rho, is 3 partial mu B nu rho. All the indices are antisymmetric in this tensor. This is the definition of the curvature. You can write this as the cyclic sum of the partial derivative of the B field. And we are always working in the string frame. We always work in the string frame. This means that we have this overall factor over here. This is the action. This action, again, describes particles. You can understand this action as an Einstein-Hilbert action plus other fields like a two-form and scalar fields. And you know that we have alpha prime corrections over here. So this is the convention that we are going to use to be very, very clear. When we want alpha prime corrections, what we want are four derivative terms. The four derivative terms are associated to alpha prime corrections at the Lagrangian level or to the action level, the four derivative terms. So just to give you some examples, if we focus, for example, in the bosonic case or in the heterotic case, the bosonic string theory or heterotic string theory at this order contains, for example, Riemann square terms plus other terms to this order, to four derivative terms. You know that, perhaps you know, I don't know, this is a two derivative action. We have two derivatives over here. Recall that the definition of R is partial derivative of the connection, a sign over there, and the connection square. So this R contains two derivatives. You have two derivatives explicit over here, and you have two derivatives over here, because you have two H. So the four derivative terms are terms related to Riemann square term, for example, for the bosonic string theory or for the heterotic string theory. You have other kind of terms. This is just an example. But the important thing here is that type 2, type 2a, and type 2b don't have this kind of Riemann square term. The corrections for type 2 starts at this order, A derivatives. For example, here we have corrections for type 2. These corrections are, for example, Riemann square term, Riemann to the fourth, plus other corrections. And at this level, alpha prime square, we have, for example, corrections just for the bosonic. And the bosonic contains Riemann cubic terms plus other corrections. So we are interested in the 4 derivative terms. So we are trying to analyze always the bosonic string theory and the heterotic. Sorry, there's a question. Only on second derivatives, the massive states.
Yeah, sorry, Eric.
Yeah.
There is a question in the chat. I don't know if you see it. Could we?
Yes, I am reading that question.
Please
if
read
you
the
work
question
with
first, otherwise people don't know what you're answering.
Okay. Sorry. Yes, totally agree. The question is, could we in principle use the massive states directly instead of the higher order derivative terms and get an action containing only second derivatives? Well, the answer to that question is that the massive state does not contribute to the leading order of the action. So we can use you can use, I don't know, the first excited mode or other excited mode directly from string theory and worked in the worksheet level. But if you work at the effective theory, so at the supergravity action, you need to, if you consider only massive states, your action is of higher order and you don't have the 2 derivative terms. You just have a higher derivative action. But I don't know if that is possible. I think that the interactions do not allow that kind of stuff. You need, I don't know, 3-point functions. You need all the terms in the Lagrangian are saying things about the interactions. At the end of the day, we always analyze the Lagrangian at from a scattering amplitude point of view. I mean, so I think you can't work in that case. I don't know if it's clear. It's a good question. So perhaps if someone else has a question, it's a good moment. And if my handwriting is not very clear, also tell me so I can write again. We are in this course, we are always interested on these 4 derivative terms, and particularly we want a systematic procedure to obtain that terms, and perhaps if this procedure is a systematic one, we can obtain other terms that could be related to a string theory, always thinking from a double field theory point of view. And in this course, we are always focusing on the 4 derivative terms. So, for example, the 6 derivative terms, only the bosonic string theory contains that kind of terms. And there's a little detail inside all these terms, is that you can always make field redefinitions. So perhaps you can work with a heterotic string theory with 6 derivative terms, but you can find a field redefinition that erases that kind of 6 derivative terms. So, for example, heterotic string theory should have 4 derivative terms and 8 derivative terms in its Lagrangian. Okay, let's move on.
Hi, Eric.
Yes.
I have a small curiosity question.
Yes.
The reason that type 2 only has the alpha prime to the 3rd, is there some intuition for it? Is it because of the amount of supersymmetries or something?
Well, I am not talking about supersymmetry, but supersymmetry, since we are not working in a superspace formulation, we here at this level, at the supergravity level, there now exists a notion of covariance or non-covariance for supersymmetry. Everything is non-covariant for supersymmetry rules. So the supersymmetry rules are enough to fix the terms in the supergravity level. And the reason why you don't have this kind of corrections in type 2, it's strongly related to supersymmetry. But at this point, that's all I can say.
Okay.
Yeah. Then perhaps I can give you some comments about how supersymmetry mixes this kind of term and why heterotic string theory has these Riemann square terms, but at this level is not pedagogical to do that.
No, okay, thank you.
You're welcome. Okay, let me move on. This is something that you already know. There exist different ways to obtaining these alpha prime corrections. We have discussed this in the first part of this first lecture in the general overview. You have beta function computations. This beta function computations says that the low energy limit or the low energy effective field theory, the low energy effective field theory, must preserve Weil invariance, local Weil invariance, and the corrections must preserve Weil invariance. This is a way to obtain alpha prime corrections. You analyze some symmetry of the worldsheet level. This is a very string theory computation. You need conformal field theory, and you need to compute, you need to preserve this symmetry. It's not important for us because we are going to work at the supergravity level. But this is an option. A different option is use scattering amplitude. Each term of the Lagrangian, of the effective Lagrangian, must agree with the string interactions always. So we have this low energy effective field theory and its corrections in a consistent way with respect to the interactions. And finally, we have these symmetry arguments, for example, these supersymmetry arguments of T-duality arguments related to a symmetry, and each term of the effective Lagrangian could be connected by symmetry transformations. We are going to see that there are some notion of covariance and non-covariance and some symmetry rules mixed term in the effective Lagrangian, so some terms could be guessed using symmetry arguments, particularly supersymmetry arguments, and of course T-duality. So in this lecture, we will focus on the last point and of course related to double field theory. So if we focus on the four derivative terms as we want, there's another point. There exists another way to compute that. It's the Birch-of-the-Roux identification. I am going to discuss about this identification in the last part of this first lecture, if I can, and if I cannot, I leave it to the second lecture. But this is another way to compute, but it is useful only for the four derivative terms. I hope I will be more clear in the future slides. So in this first part, I will continue talking about the low energy effective field theories. And in the second part, we will focus on the four derivative corrections. So let's back to this action. This is the supergravity action. And this action is invariant under different symmetries. For example, abelian gauge transformations. Here is what Gianluca was saying about the notation. This parameter for Gianluca was lambda, and I am using a zeta over here. I think that today that's the only difference between Gianluca's lectures, but just let me know if something is different. At this point, this symmetry transformation acts only on the B field, and if we compute, for example, the transformation rule for the, sorry, this is not clear. If we compute the transformation rule for the curvature, H mu nu rho, what we have to do is to write the definition and to use this transformation rule. We use it. And here you can see that we have a symmetric term with derivative. This is symmetric in derivatives. So this quantity is 0. This means that this three form is gauge invariant, is abelian gauge invariant. If this term is gauge invariant and these terms do not transform, then the Lagrangian is gauge invariant. Recall that the Lagrangian is this one. This is the Lagrangian. This is our Lagrangian. The Lagrangian is gauge invariant and the action is gauge invariant. So we have this symmetry over here, but this symmetry is not useful to construct alpha prime terms, for example, because this symmetry does not fix these coefficients. These coefficients over here can be, I don't know, instead of a 4, I can put over here a 6, and this is still gauge invariant. The same for the -1/12. I can write over here a 20, and this is gauge invariant. So this symmetry is not useful. This symmetry does not mix terms at the Lagrangian level. So it's not useful to construct alpha prime corrections. So let's analyze another symmetry. This symmetry, diffeomorphism, was already discussed by Gianluca. So this part will be easy for you. In this case, if we focus on the Lagrangian, the transformation of the Lagrangian is given by, sorry for the notation, the transformation of the Lagrangian is given by the Lie derivative of the Lagrangian, and this object transformed as a scalar. This is a transformation with no weight equal to 0. So if we transform each term of this Lagrangian using infinitesimal, these are infinitesimal, using infinitesimal diffeomorphisms, the Lagrangian is not invariant, but the action is invariant. The Lagrangian is invariant modulo a total derivative, or up to total derivative. The Lagrangian is invariant up to total derivative. The action is invariant. This is a symmetry. This symmetry is not useful to construct alpha prime correction. And the reason that this is not useful is that, again, each term of the Lagrangian is a scalar. This term is a scalar, transformed as a scalar. This term transformed as a scalar, and this term transformed as a scalar. So we can, again, change the number, the coefficients of the Lagrangian. Again, we can change this number, the numbers over here, and this is the still diffeomorphism invariant action. So it's not a very good symmetry to look for alpha prime corrections. The symmetry that we are going to use in the next lecture is T-duality or ODD-R symmetry. But let's talk about that in the next lecture. So at this point, we know that the diffeomorphisms require a covariant derivative, since the partial derivative of a vector of a one form does not transform as a tensor. We have this over here. We have that the transformation, we know that the transformation of the partial derivative of a one form, for example, does not transform as a two form, does not transform in a covariant way. We have an extra term over here when this derivative acts. You can do this computation when you want. When the partial derivative acts on this term, we have a non-covariant term over here. This is this object over here. This object does not transform as a tensor, so we need to introduce a new notion of derivative, a covariant derivative with a new term over here in order to fix that problem. We call that the transformation, the non-covariant part of the transformation of this object of the Levi-Civita connection. We are always using the Levi-Civita. This is the Levi-Civita connection. The non-covariant part of this transformation is the partial derivative of the parameter. So this connection is useful to construct a covariant derivative. This is a good connection. The transformation rule of this connection cancels the non-covariant part of the derivative of a one form or a vector. So this is a good connection, at least for this symmetry. And we don't need a connection for the previous symmetry. For the abelian gauge transformation, we don't need a connection in that case. So for now, for this moment, we have only one connection, and this connection is due to diffeomorphism invariance. So let's continue. Let's continue with the closure. here you have the computation of the closure. This is very similar to Gianluca's lectures, but he computed the closure for the DFT transformation, and this is the closure for the ordinary diffeomorphisms transformation. And the bracket in this case, this parameter over here, is called the Lie bracket. This is the Lie bracket. This Lie bracket is saying that when we compute the bracket, when you apply two transformations in different order acting on a vector or a tensor, a generical tensor, this computation must close. This means that we need to find a new parameter over here. This is a new parameter. It's a parameter contracting with this other derivative. We have a contraction over there. This acts as a new parameter, and we always need to satisfy closure conditions for the different symmetry rules of the Lagrangian. This is important. Of course, we need to the mixed computation. For example, if we mix diffeomorphisms with abelian gauge transformations acting on the B field, for example, that kind of computations should be guaranteed. Perhaps you can do that as an exercise. But we always need to compute this kind of closure consistency rules. In here, you have in red terms that cancel, and you finally obtain the Lie bracket. I am not going to discuss about the computation, but if you have any question about this computation, you can write on Slack, and we try to reach to the final result. We have a Lie bracket over here. And an important point is that we are working always with this action. This previous action is this action. I can write the Lagrangian again. This Lagrangian, that is e to the r plus blah blah blah. We have this Lagrangian, or the integration of that Lagrangian. That is the previous action. The previous action. I can highlight. Sorry. And this action, this previous action, is called the universal sector, or the fields in this action are the universal sector, since are the massless modes of the bosonic string, as you already know, but also describes the dynamics for the massless modes of the NS sector of type 2. This means that part of type 2 superstring is described by this Lagrangian. Recall that for in the first case, we have d equal 26, and in the second case, we have d equal 10. That's the only difference, the number d, the number of the critical dimension. The Lagrangian is exactly the same. And finally, this Lagrangian is useful to describe the bosonic and gauge part of the heterotic supergravity action. So this Lagrangian is useful for bosonic, is useful for the NS sector of type 2, and is useful for the engaged part of the heterotic supergravity action. So this means that we have a gauge part over here. We have a gauge part in the heterotic supergravity action. And I am going to show you the form of these extra terms in the heterotic supergravity action. This extra term are due to an extra field, an extra massless bosonic field in the spectrum of the heterotic supergravity action. So this extra field is a gauge field. This is the gauge field. Let me get back to yellow. This is an extra gauge field, is a bosonic massless field. This field, they form the Lagrangian. We have a Yang-Mills term over here. The contractions of this object, the contractions here, the construction are given by a Cartan-Killing metric or an inverse metric. This is a Cartan-Killing inverse metric. And let me observe that we have a deformation on the 3 form. We have a different 3 form when we consider heterotic supergravity. In heterotic supergravity, the 3 form is defined in this way. We have an extra Chern-Simons 3 form with which depends on the A field. Of course, if you consider the gauge field A equal to 0, we go back to the ordinary supergravity action for type 2, the NS sector, the universal sector, just in the case that this extra bosonic massless field A mu I is 0. Just in this case, we turn back to the ordinary case, the usual case. But we have to consider this kind of contributions if we work in the heterotic supergravity. So we have a Yang-Mills term and Chern-Simons terms, and of course the curvature is over here. We have this object is the curvature of A mu I. The curvature is the field strength. The field strength is F mu nu, and this is behind this Lagrangian. There exists a new symmetry that is a non-abelian gauge symmetry, and that's the reason of this structure constant over here. We have structure constant because this new Lagrangian, this heterotic supergravity Lagrangian, is invariant under the same symmetries than before, diffeomorphism and abelian gauge transformations, but now we have a non-abelian gauge transformation to consider. So why this Lagrangian is still invariant under the previous symmetries? Why this Lagrangian is invariant under diffeomorphisms? For example, the reason is that the transformation of this field is a one form, and the transformation is given by the Lie derivative. So if you perform the computation, the diffeomorphism invariance is guaranteed at the level of the action. Recall that the Lagrangian is invariant up to a total derivative. So this symmetry is okay. About abelian gauge transformation, the Lagrangian is invariant because the transformation under this symmetry of the A mu I is 0. The abelian gauge transformations only affects the B field. So this abelian gauge transformation is guaranteed again. And finally, we have non-abelian gauge transformations, and these non-abelian gauge transformations affect only to the gauge field, the A field, and the B field. And these transformations, in this case, these transformations are non-covariant. These transformations are non-covariant. Why? Why these transformations are non-covariant? Well, a covariant transformation has this form. This is a covariant term. For example, in this case, we have an extra term over here, an extra non-covariant term. So this field, the massless new field, this A field, the gauge field, transform non-covariantly and particularly transform as a connection. This transformation over here, it's a connection transformation, transforms as a connection. So for example, this new field, this A field, can be used as a connection if we want to construct a new covariant derivative. What kind of covariant derivative? A covariant derivative under this new symmetry, under this non-abelian gauge transformation. So this field is useful to construct a connection. And finally, the transformation of the B field is called a Green-Schwarz mechanism. This is a Green-Schwarz mechanism. This is a Green-Schwarz mechanism. And now we can see why the three form is deformed, why we have a different three form. Let me go back just for a minute. Why this three form over here is different. We have Chern-Simons term over here because the B field transform this way under non-abelian gauge transformation, and we need a new three form, this three form that under this transformation, we are using this parameter lambda as a non-abelian gauge parameter. We need this. an invariant, this means that H bar is non-abelian gauge invariant. H, just H, the derivative of B, just H is not non-abelian gauge invariant. We need extra terms in order to obtain this. So H bar is non-abelian gauge invariant. That's the reason why we have to deform the curvature and introduce Chern-Simons terms at the supergravity level, and particularly to deform the curvature of the B field. We need a new field strength in order to have a non-abelian gauge invariant field strength. That's the reason. So questions up to here. In a few minutes, we can do a break, but let me finish with this idea. I don't know if someone wants to ask for the microphone, I can ask questions. I don't know if this is clear. I am using a lot of colors, but I don't know if this is pedagogical or not. Okay, let me go on, and if there's a question, you can ask. So as you know, a generic gauge vector transform covariantly in this way. This is the covariant transformation of a vector, a gauge vector, an object with an I index. Recall that the contractions are given by the Cartan-Killing metric. Here, the contractions are given by the inverse Cartan-Killing metric, and this is constant. It's a constant metric. This is the metric and this is the inverse. Both of them are constants. Of course, the structure constants are constant. So, for example, when we want to transform the derivative of a gauge vector, we obtain two contributions. We obtain this first contribution when the derivative acts on the parameter. We have this first contribution over here, and we obtain a covariant contribution. The other contribution is a covariant transformation. So we need to cancel this term in order to construct a covariant derivative. We need to cancel this term, and this is what we are going to do now. We are going to construct a new covariant derivative, a different one, a covariant under this new gauge transformation. And as we have said, we can use this A field as a connection. So we still use this symbol over here is the same symbol when this is always our covariant derivative, and the kind of connection that we use depends on this object. If this is a gauge vector, we have a gauge connection over here, and if we have a mixed contribution, for example, something like this, if we want the covariant derivative of a tensor of some object with a gauge index and a space-time index, this object over here will have the Levi-Civita connection and the A connection, and we apply this to this object. We always use the same notation. We use the nabla notation, but this nabla over here contain different connections depend on the nature of the object that we have over here. If we have different indices, we include always the connection that we need in order to that object be covariant. That is our convention. Same symbol. If we start constructing different symbols, it's very complicated. Just one symbol is the most simple case. Okay, and particularly in the next slides, I show you that this object transforms covariantly, of course, as expected. We expect that the curvature to be covariant, and this is covariant under gauge transformations. This is the computation. This is part of an exercise, so you have the answer over here. You can analyze this wherever you want. These slides are on Slack, on the Slack channel, so you can try to analyze this computation. It's very straightforward, 4 lines, but you need to use this this final relation that it's a Jacobi identity. This identity is in the exercises, is given. It's related to a property of the structure constant, but I don't want to discuss this in this moment. Let me go on. And this is the field by formalism, but this is a good moment to have a little break. Let's take a 5 minutes break. And if I think that is 12:50 for you. So 12:55, we can continue. And in the next part, I am going to discuss about the field by formalism and about the 4 derivative gravitational terms that corrects the low energy limit of string theory. If there's a question, of course, I'm here.
Thank you, Eric.
Is the field line, but you can understand this field line as the square root of the metric tensor. We have this relation over here. The field line is like the square root of the metric tensor, and the same for the inverse field line. Now the flat indices are contractions with a new metric that is a Minkowski metric, an invariant, a constant metric. This is a Minkowski metric. And this means that when we want to write a supersymmetric invariant theory, we need to use this field line, and we have another symmetry. For example, in heterotic string theory, we have diffeomorphisms, abelian gauge transformations, non-abelian gauge transformations, and now we have Lorentz transformations. These are Lorentz transformations. Why we need these Lorentz transformations? Because we are writing things in terms of the field line. And why we write things in terms of the field line, for example, for the heterotic case, that's because this theory is n equal 1 invariant. So we need to write heterotic string theory in terms of the field line. This field line formalisms is completely necessary for introducing the fermionic fields. We know that these fermionic fields are present, are always present in the heterotic string theory, so we need to write things in the field line formalism. So we have a new transformation. This is the new transformation, is the Lorentz transformation. And the Lorentz parameter, I use lambda as a Lorentz parameter, so this is in Gianluca's lecture, this lambda was a DFT parameter for diffeomorphisms, for generalized diffeomorphisms. I am always using lambda for Lorentz transformation, so be very careful, please. And if you have any doubt, just ask. But this is a Lorentz transformation. This is Lorentz transformation, and particularly the Lorentz parameter is antisymmetric because we need to ensure this condition. This metric is a Minkowski metric, so the transformation is 0. So in order to obtain this kind of relations, the Lorentz parameter is antisymmetric. This is a Lorentz transformation. Okay. So we have a new symmetry, and again, we need a new covariant derivative. This part is important. I know that it's very redundant because we always need a new derivative, but this is a very important derivative. This derivative is present when we want to derive a flat vector as this. And if we try to analyze which is the transformation of the derivative of a vector, this transformation contains an extra term, a non-covariant term. This is a non-covariant term, this term over here. This is the non-covariant term. So we construct this covariant derivative, and we need that the transformation under Lorentz transformation of the spin connection, we need a covariant part and a non-covariant part. The non-covariant part is this. This is the non-covariant part of the transformation, plus, and we have the covariant part. This is the covariant part. Okay, so this transformation is a non-covariant transformation, and this is the covariant transformation that acts on the flat indices. So the important part is that we need to cancel this term. So we need this non-covariant transformation over here. I think this is part of an exercise. We can check the exercises later. This is the transformation. And an important point here is that if we want to know what is this object over here, what is this spin connection? This is the spin connection. This is the spin connection. The spin connection, if we demand field-by incompatibility, this is the field-by incompatibility, the covariant derivative acting on the field-by, we want that this covariant derivative to be 0. So, and recall that we have two indices over here. We have a space-time index and a flat index. Recall that mu and nu are a space-time index that runs from 0 to d-1, and A, B, C, D are flat indices that runs from 0 to d-1, sorry. And we have two connections because we have two indices. This field transforms as a vector. The transformation of this object over here, it's a vector. It transforms as a vector with a Lie derivative and the diffeomorphisms, and we have a Lorentz transformation like this. This A is the same of this A. I am writing in a different way, but it's the same. I can use this. Okay. So we demand this compatibility condition, and then we can find the form of this object, because the form of this object is related to derivatives of the field-by. We have derivatives over here, and we have derivatives over here because we always can write the metric tensor in terms of the field-by. So we have a spin connection, a well-defined spin connection, and try to find the explicit form of this spin connection in terms of the field-by is also part of the exercises. I think that in the exercises we use this other notation, ABC. This is the same ABC, and this is the same object, but we have over here a field-by with this combination. So I think that the exercise is to find this in terms of the field-bys. Just check the exercise list, you will find it. So let's try to move on. If we work in the field-by formalism, now our Ricci and Riemann tensor, our Riemann tensor now can be written in terms of the spin connection instead of the Levi-Civita connection. And this Riemann contains the same information that this other Riemann. It's the same object. And finally, we can define the Ricci tensor and the scalar taking traces, as you know. So this is the field-by formalism, and you can use this formalism in general relativity. It's an important formalism when we work in supergravity theories, because if you want to introduce the super part of the supergravity, the super partners, the fermionic fields, you need to work in this field-by formalism. And the reason of this field-by formalism is that we need to construct a Clifford algebra, and a Clifford algebra requires a Minkowski metric or a flat metric. So we need to introduce this formalism always for example, the heterotic case. So here you have the exercises. Many of the exercises, all the exercises are on the Slack channel, and many of these exercises were on these slides. For example, the closure of the transformations, the computation about the F field strength transformed covariantly under non-abelian gauge transformations. Some of these exercises are on these slides, are explicitly done. And the same for this, you have the answer to this transformation. You already have the answer, and here you have the spin connection in terms of the field line. This is the form of the spin connection. You can check, for example, that the spin connection is always antisymmetric in its last two indices. This is another exercise that you can do. It's very simple. You can see that it's antisymmetric. It's very quick. And here we have summarizing for the first part of this lecture. In this part, we have studied the low energy limit of bosonic string theory. We have studied a low energy limit. And the bosonic truncation of heterotic supergravity. Why the bosonic truncation? Because we are not including the fermionic fields. We focus on the massless field content. We have this G, V, and phi. We have an extra bosonic field for the heterotic case. Of course, in the heterotic case, we should write this E over here, this field line. I should write it in red. Let me write it in red. We have a field line over here instead of a metric because we have the field line formalism. We have analyzed the symmetries. We have diffeomorphism, invariance, abelian gauge transformations, non-abelian gauge transformations, and Lorentz transformations. These Lorentz transformations are implicit, for example, in the bosonic string theory. We can always use this field line formalism for the bosonic string theory, but it's not necessary. And finally, we review the action principle, and in the case of the heterotic string theory, in the heterotic supergravity, sorry, in that case, we have a Young-Mills contribution, F squared terms, and the field strength of the V field, the 3 form, is deformed with Chern-Simons terms. This is just a kind of, this is all what we have seen in this first lecture. And I'm going to move to the second part, and let me know if there's questions. I can read the chat if somebody has a question. It's a good moment, and in a few seconds we are going to start with the 4 derivative terms, with the alpha prime corrections for the bosonic string theory and for the heterotic string theory. Okay, so far so good. So let's move. Let's move. Gravitational 4 derivative corrections. So let's try to understand this slide. We have a lot of information over here. So let's try to understand this. So here we are considering 3-point and 4-point function scattering amplitudes. We are considering scattering amplitudes. This means that this is the part of the Lagrangian of string theory when one starts integrating out the massive modes. We have 4 derivative terms. Observe that these are 4 derivative terms. We have Riemann squared term over here. We have Riemann term and H squared term. We have H to the 4th. This is the square term of this other definition. We have H square. We have different terms over here. And this is a compact form to write both the corrections for the bosonic string and the heterotic string. Observe that the parameters A and B, I can change color perhaps. The parameters A and B, these parameters have to be fixed in this way. Here you have the parameters. You have to fix the parameters to find these alpha prime corrections. The alpha prime corrections appear when A is equal to -1 and B is equal to -1. That's bosonic string. And the alpha prime corrections appear when A is equal to -1 and B is equal to 0. These are alpha prime corrections. For other combinations, if you took, I don't know, A equal to 0, no, not that case, but if you took, I don't know, A equal to -1 and B equal to 2, that is not an alpha prime correction. It's a possible correction to a supergravity theory, but it's that kind of correction that does not respect While invariants, scattering amplitudes, it's very different with a string theory. It's just a particle theory with higher derivative corrections. So the important point here is that higher derivative corrections is not exactly the same as an alpha prime correction. Higher derivative terms, there's a lot of possibilities, but alpha prime corrections, we have alpha prime corrections just in these cases, for the bosonic string and for the heterotic string. I hope this is clear because this is important. We always can include, I don't know, higher derivative terms in an Einstein-Hilbert action. We can include, I don't know, a Riemann square term with a very strange factor, and that's not coming from string theory. It's just a correction to a particle action. In a string theory, these are the terms with these particular coefficients. These are the alpha prime correction, the gravitational four derivative corrections. This is very important. And let me observe that we have a special case over here. This special case is related to a kind of Chern-Simons three form. This is a kind of Chern-Simons three form, but this is a gravitational Chern-Simons, and this gravitational Chern-Simons appear only in the heterotic string because we have A minus B, so the bosonic string does not contain this term. This term over here is a very particular term in heterotic string theory. It's a Chern-Simons term. I have a question. So for other values of A and B, they would be a general relativity theory without a UV competition. That's right. I don't know the part of the UV competition because I don't know, we can work with I don't know, a higher derivative supergravity, and we can start computing loops. I don't know. There are cases that not necessarily came from string theory, and we already don't know if they have or not a UV competition, but it's near to a correct. It's a good question, and the answer is that I don't know the part of the UV competition. If that makes sense, thank you. Okay. Okay, we can construct higher derivative terms. We have other options of A and B, but the options for the string theory for the four derivative terms are these options over here. For bosonic string, A equal to -1 and B equal to -1. And for the heterotic string, A equal to -1 and B equal to 0. These are the terms. Of course, since type 2 superstring doesn't contain this kind of terms, the election of the choice 0, 0 is a kind of alpha prime correction because it's a trivial one. We are not going to talk about type 2 in these lectures. We are always focusing on the bosonic and on the heterotic cases. So this is, I was saying that this is a three form. This is a Chern-Simons three form. This is a three form. It's a Chern-Simons, but it's a gravitational Chern-Simons term, and this will be important. Observe that the connection over here is the spin connection. This is the spin connection, and it's not the A field, but it's a Chern-Simons term. Okay. Perhaps if there is another question, I can answer in this moment. Let me drink water. Okay, we want to recover this kind of terms from double field theory. We already know these terms, but we want a systematic procedure from double field theory to construct these terms, and if we can, beyond this order. We want a systematic procedure, perhaps a non-perturbative procedure that would be the best, in order to obtain alpha prime corrections in an easy way. You know, scattering amplitudes and beta function computation, when we work with arbitrary manifolds, not in the flat case, in an arbitrary metric tensor or in an arbitrary manifold, this computation, the scattering amplitudes and beta function computation are really, really hard. That's why I want to use double field theory to obtain this kind of terms. I want to use a simpler or a simple procedure to obtain this kind of terms. So let's move on. Okay, so far, sorry, in the last slide, in this slide, I have to mention that this empty, it's for Metsaev and Seitlin, empty over here. And if you look my notes, this, let me check in my notes. This is reference 7. It's a very interesting paper to read. This is reference 7 in my lecture notes. Reference 7, it's Metsaev and Seitlin. And if we consider this kind of corrections to the supergravity Lagrangian, if we include this term over here with 4 derivative terms, A and B completely arbitrary, A and B arbitrary, this kind of action requires, this kind of action, let me back to the yellow, this kind of action requires a first order Lorentz transformation. So let's try to understand this point because it's very important. If we want to transform, if we want the transformation with respect to Lorentz transformation of this new Lagrangian, we have that the zero order transformations, the standard Lorentz transformations, transform this term, transform L1 empty. This is a 1. Lorentz transformations acts non-trivially on this term. This term is not Lorentz invariant. Why is not Lorentz invariant? Because we have a lot of spin connections over here. The connections are not covariant. This transformation is not covariant, it's non-covariant, and we have this contribution over here. So the full Lagrangian, the full first order Lagrangian, the Metsaev-Seitlin Lagrangian, this Lagrangian over here is not invariant under Lorentz transformation. So this is not 0, and therefore we need to deform the transformations. We need to include higher order transformations. This delta 1, lambda is a higher order. This is a higher order transformation, higher order Lorentz transformation. We need to include this kind of transformation, and we need to transform something in the zero order Lagrangian. Let me write in this way. And this term, if we have luck, this term should compensate the other one. This full transformation must be 0. So we need to include this kind of new transformations. We have this kind of new transformations over here. We need new transformations in order to the full Lagrangian with 2 derivatives and 4 derivatives be Lorentz invariant. We need new transformation. This is completely necessary. And the reason is that these Chern-Simons terms transform under Lorentz transformations. So this is important. So if you have questions, just ask, because this is very important for the lecture. And let me check. Okay, we are okay. Let me move on. So this deformation, this delta 1 over here, acts only on the B field. We include a Green-Schwarz mechanism for the B field. This is a higher order, first order transformation. Now Lorentz transformations act to 0 order and act to first order. This is a first order. This is the only field that we need to impose a new transformation, a higher derivative transformation, to cure this new problem that we have. And particularly, let's observe that a 0 order transformation contains no derivatives. Recall that the 0 order transformation, this 0 order transformation, the 0 order transformation is something acting on a B. It's B times lambda. This is a 0 order. We don't have derivatives over here. And a first order Lorentz transformation has 2 derivatives. We have 1 derivative over here and 1 derivative in the spin connection. The spin connection contains 1 derivative. So the first order transformation only acts on the 0 order Lagrangian. So we are going to transform, for example, this object over here. We are going to transform the H bar to first order. This transformation is not zero anymore. We deform the V transformation, and therefore we, in consequence, we have things like this.
Eric, just to let you know that you have about 10 minutes left.
Yes. I know, and thank you very much. So here you have the computation. It's a very simple computation. It's very quick. Here you have the detail. The transformation of the H field. Sorry, I have written a bar over here, and we don't need a bar over here. This is I have the ordinary three-form field strength, and if we transform, we using these new transformations, the zero-order Lagrangian, and we sum the transformation of the zero-order transformation acting on these new terms, these transformations cancel. So this Lagrangian is invariant when we consider four derivative terms if the V field transform with a Green-Schwarz mechanism that has, well, you know the form. This is the form of the Green-Schwarz mechanism. This is the Green-Schwarz mechanism. It's a gravitational Green-Schwarz transformation. And this means that the V field transform with a two derivative transformation under Lorentz transformation. You can see the computation later if you want. It's very easy. And the main point here, perhaps, is that the previous Lagrangian, the Metsaev-Seyton Lagrangian, can be written in this form. This is a new form to write the four derivative terms, but this Lagrangian over here is related to string theory. The four derivative terms over here are exactly these numbers over here. I have highlighted everything, but these numbers over here are exactly what we need when A is equal to -1 and B is equal to 0 for the heterotic case, or A is equal to -1 and B equal to -1 for the Bosonic case. But this is just a field redefinition. This Lagrangian over here is due to Virchow-de-Roux, and this Lagrangian is exactly the same as the Metsaev-Seyton Lagrangian, but we need to consider covariant field redefinitions and non-covariant field redefinitions.
Eric?
So,
I
sorry?
have a question about the physical interpretation of this first order Lorentz transformation. I mean, how can I think of it? What's the physical interpretation?
About this Virchow-de-Roux Lagrangian?
About the having zeroth order and first order Lorentz transformation.
Okay. The physical interpretation of a Lorentz transformation is not very easy, because the Lorentz transformation, we know the infinitesimal form of a Lorentz transformation, for example, and an infinitesimal, we know the Lorentz group, we know everything about the Lorentz transformation, but the two derivative Lorentz transformation, the Green-Schwarz mechanism, is, we know that it's very, very necessary to work with phenomenological string theory, for example. This mechanism is very important to heterotic string theory. In fact, this mechanism is related to a revolution in string theory in the 80s due to Green and Schwarz. And the physical point of view is a kind of, it's difficult to see, because we don't know the infinitesimal form about this Green-Schwarz transformation, so it's very, very difficult to have an intuition about this transformation. But at the end of the day, we can analyze this kind of Lagrangian transformations from a Noether procedure. If you recall that Noether transformations are related to conserved charge and that kind of stuff, these kind of symmetries are always saying things about the conservation of this kind of Lagrangian and the relation between different terms in the Lagrangian. I don't have an exactly answer to the question. It's a very good question. And we expect higher order symmetries when we introduce higher derivative terms. So it's expectable to find new symmetries at different orders.
Okay, thanks.
No, you're welcome. It was not a very good answer, sorry. Another question? it's important to note that I think that there's another question.
Yeah, hello. I wanted to ask about the closure of the corrected alpha prime Lorentz transformations. Is it okay, or do we have to calculate something and see?
Yes, an excellent question. We always need to satisfy the closure conditions. I think that in my lecture notes, I haven't included the explicit computation. It's a very good computation to a new exercise. You can add that as an exercise, but it's completely okay. This new Lorentz transformation satisfy closure conditions, but the new parameters, the parameters 1, 2, or for example, in Gianluca's notation, I think he used the lambda 3. This kind of parameters now contains higher derivative contributions. You have parameters with, for example, I don't know, 2 derivatives in the bracket. But it's a very good question, and the closure conditions are completely guaranteed.
Okay, thank you.
You're welcome. So in this new Lagrangian, we have this version of the Roux Lagrangian. It's exactly the same as the Metsaev and Seitin Lagrangian, but we have a difference over here. For example, we have a new three form. Again, we need to deform this 3 form. We have over here this new 3 form with gravitational Chern-Simons term. Recall that this kind of 4 derivative terms are gravitational 4 derivative terms. This means that if I want to introduce this in the heterotic case, I have gauge Chern-Simons terms in order to have a non-abelian gauge invariant 3 form, and now I have this new Chern-Simons gravitational terms. This, in the case of the heterotic case, we are not analyzing 4 derivative terms for the gauge part. We are not analyzing, for example, F terms to the 4, corrections to the Yang-Mills action. We are just focused on the gravitational terms. So in this version of the Roux approach, the 3 form is the form with Chern-Simons term, as you can see over here, and the connection now has torsion. We have a torsion term. This torsion term does not affect the way the connection transform because this term is completely covariant. The H field is covariant under Lorentz transformation. This notation over here means that H mu AB is equal to, sorry, I don't have space over here, is H mu rho and A nu E nu A E rho B. This is the definition of this object over here. This is just a field redefinition. It's the same theory. We have heterotic corrections and bosonic corrections when in the same cases A and B from the previous Lagrangian. And finally, this action is invariant if we impose a Green-Schwarz mechanism, but the Green-Schwarz mechanism is slightly different. We have a new contribution over here. We have 2 terms instead of 1 term. This means that both B fields are different. They differ in this term. I think that it's part of the exercises to prove that these transformations are okay, or this is consistent. We use always this kind of non-covariant field redefinitions to change the transformation rule of a field. So in this case, if we want to start from the Metsaev-Seitin Lagrangian and reach the new Lagrangian, the version of the Roux Lagrangian, we need to relabel our fields. We need field covariant redefinitions and field non-covariant redefinitions. So for example, in this case, in the heterotic case, we have this form. This is the heterotic sugar action. I am just choosing the parameters A equal -1, and I have this new Lagrangian. I have 4 derivative corrections. We have this kind of Riemann square term, but this Riemann is constructed. Recall that this notation minus over here, let me change the color. This minus over here means that we need to construct this Riemann tensor using this new connection that contains torsion. So the H to the 4 terms or Riemann times H squared term, all that terms are in this compact notation and are inside that term. This is the form of the version of the Roux action for the heterotic string theory. This Lagrangian will be very important because we are going to connect double field theory with this Lagrangian. And I think I am going to stop over here. Here you have the Green-Schwarz mechanism in terms of this connection. But I'm going to stop here because it's my time. And in the next lecture, in lecture number 2, I will start here. I will finish this part, and then I will start with the double field theory part. So thank you very much. And any question can be written over here or on the Slack channel.
Thank you very much, Eric, for the nice lecture. Very well, then now we'll have our lunch break for 1 hour and a half. We come back at 3 Central European time. Thank you again, Eric.
You're welcome.